Hello and welcome to Lecture 4, where we're going to talk about the demodulation of AM. So last week we spoke about amplitude modulation. We spoke about a particular type of amplitude modulation called double sideband large carrier. And today we're going to talk about demodulation. So demodulation is how to extract the original message from our bandpass signal. So how to recover the baseband signal from the bandpass signal. So it's the opposite of modulation. Now our next lecture, which I'll actually release tomorrow, is going to be about other variations of amplitude modulation, DSB, SSB and VSB, and then we'll talk about demodulating that in lecture 6. So all of these first 6 lectures, these will be included in the class test on the 17th of March. Okay, so lectures 1, 2, 3, 4, 5 and 6, all to be included in that class test. So this is where we are now, week 4. What I'm going to do is to bring this class or this lecture forward to Tuesday so that you have that ready for the problem class on Wednesday. Okay, so that gives us plenty of time to prepare for our class test on the 17th of March. There's been a slight alteration to the schedule. The 3rd of May is a bank holiday. So that means there's no classes on that day. So what I've done is I've moved the problem class that was planned for that day to the Wednesday, and I've moved the Wednesday problem class to the following Monday. Okay, so this bit has changed in your schedule. So just make a note that the 3rd of May is a bank holiday, so we're not having a problem class on the 3rd of May. Okay, so recap from last lecture, we introduced amplitude modulation, the idea of amplitude modulation, how it is that we encode the information from a low frequency baseband message onto a high frequency or higher frequency radio frequency carrier. We spoke about the depth of modulation, and we called that the Modulation Index, and we gave an expression for that and how that expression can be found from the shape of the signal envelope. We spoke about how the Modulation Index needs to be limited between 0 and 1, and the closer it is to 1, the better. We spoke about the spectrum of AM, and we said that the bandwidth of the bandpass signal is twice the bandwidth of the original signal. So if you have a baseband message signal of bandwidth FM, then the AM signal will have twice FM as the bandwidth. And we said that the carrier component is particularly powerful in AM. That's why we call it DSB-LC. Today we're going to look at some of the implications of this large carrier component. But first we're going to talk about demodulation. That is, how can I recover this original message from the AM signal? So how do I detect the signal from this envelope? So we're going to talk about envelope detection, and that is an example of asynchronous detection. Another word for asynchronous is non-coherent. So if you see these words, they refer to envelope detection. So what it means basically is we don't have a local oscillator. We don't have a local RF generator. Okay. Later in the lecture, we'll talk about power considerations and power efficiency, and we'll then have a problem class. It says Thursday, but we know it's not Thursday, it's Wednesday. next week, actually brought forward to Tuesday, we'll be talking about the remaining members of the AM family. Double sideband suppressed carrier, or just DSB, single sideband, and vestigial sideband, VSB. Okay, so remember we spoke about the modulation index, and we said that the modulation index is generally less than 100%. So when the modulation index is less than 100%, you have this envelope where the maximum and the minimum don't overlap. So there's always some carrier component. As we increase the modulation index to 100%, you notice that you have instances where the amplitude of the carrier is 0, because you have the peak and the trough of the envelope touching but not overlapping. Now, if we were to exceed 100%, so if M was 1.3, 1.2, greater than 100%, you would then have this situation here where the lower envelope is overlapping with the upper envelope. And what that gives you is a phase reversal. So right here, the phase has undergone a 180-degree shift. And that is a form of distortion, isn't it? So this is a distortion, and therefore it's undesirable. Okay, so what we want is our modulation index to be less than 1, or even equal to 1, but never more than 1. So remember this slide? We said if we have a low frequency baseband signal, M of t, and I've chosen M of t to be a simple cosine, even though it doesn't really look like it's a sine wave there, but it doesn't matter. And we have our high frequency carrier here. Remember, this contains no information, or no useful information. This is simply a vehicle to convey the message. And inside the modulator, inside this AM modulator, we have two processes. We have clamping, and by clamping I mean adding DC. So add DC, that's called clamping. And we have multiplication. And that's how we end up with this AM signal with our message encoded into this amplitude. So the question we want to answer today is, how do we recover this low frequency envelope from this high frequency message, or high frequency bandpass signal? So this process of recovery is called demodulation. So this is a little YouTube clip I wanted to share with you. It's about so it's a little project where this guy builds a envelope detector. So it's only 3 minutes long.
Hello and welcome to Weekend Projects. I'm Bree Pettis, and every week I bring a project that you can make over the weekend. This week we're going to make a foxhole radio. During World War II, GIs got really clever and made up really cool radios that were super simple so that they could listen to radio stations. There were German stations you could listen to, and sometimes you even got lucky and heard an English station. To make this project, you're going to need a toilet paper tube, you're going to need a safety pin, a bunch of thumbtacks, and a razor blade. Oh, and you're going to need some magnet wire and a board to put it all on, plus an antenna, which is just a long wire. I'm just going to use some wire I scrounged out of a Cat 6 cable. And you need, for the ground, I'm just going to use some of that same wire as well. Alright, let's make it. For the coil, I'm using magnet wire. That's because it's got a non-conductive coating. GIs in the field would have found stuff like this in motors, or they could have just used regular wire and coated it with varnish. You can attach it with tape before you wind it up, or put a hole in it and tie it on. That'll keep it from slipping as you wind it up. I'm trying this again, and I've poked a hole in here so I can tie the wire on, and now I'm just going to slide this over the drill press. It's going the wrong way. That definitely didn't work, and so I tried it with a hand drill, and that definitely didn't work. You've got to hand wind this thing. The next thing I did is I put the whole thing together according to this schematic. I'll include this in the PDF so you can check it out. Alright, so I've got my coil here, and I'm using paper clips and thumbtacks to attach things together. There's no soldering involved in this project. You can just wire everything up. This is the detector, and it's got a cat whisker and a razor blade. What you've got here is you've got a safety pin and a little pencil lead here. This hooks up to the antenna, this hooks up to ground, these hook up to the earphone, which I've got right here. Okay, now I just tried this out and it didn't work. And I think the reason why is that this razor blade has been blued. They used this special type of blued razor blade back in World War II. And blued razor blades, basically what that means, it's been heated up really hot so that it turns blue, and I think that makes it stay sharper longer. So I'm going to have to actually make this blue myself. I've got this all set up on metal so it won't burn, and I've got it in vice grips attached to little clamps that are attached to the razor blade so that this can get as hot as possible and not get a lot of heat going this way. Let's try this out. Alright, now I'm by the window, and I'm doing that because I've got the antenna going out the window and the ground hooked up to the radiator here as a ground. And what I've done is I've taken the little cat whisker and I've adjusted that, and now through the earphone I can hear radio. It's like a talk radio show. I can just faintly hear it, but it's enough to understand it. Okay, I'm going to go ahead and hook this up to the camera. I've attached a little jack from a headphone, and I'll plug this right in.
Because I didn't catch it. But the point of the matter is, I would have said to Belichick, knock it off. Don't try it on me.
Yeah, you know,
and if he did it, I'd set it up that he got caught. But I would at least give him a chance to knock it off.
This is a great project for you to get started in radio. This is the same radio that GIs used as they were in foxholes in Europe. And it's really simple and really fun. And it doesn't use any batteries. All the power comes straight out of the air, the radio waves. Okay, go out there, make yourself a radio, have a great weekend.
Okay, so that was really interesting. So you noticed that everything in there was analog electronics. All we used was some very simple components. 1, 2, 3, 4. So 4 components with no battery. We were able to recover AM radio. So as he said, this is the kind of radio that soldiers used in the field to pick up radio signals, to be able to listen to the radio. They didn't have access to advanced telecoms equipment, but this is what they used during the Second World War. So that's why they call it a foxhole radio, but what we're going to call it is an envelope detector. And we'll look at the electronics of the envelope detector in a second. So we're talking about a detector which is a demodulator. It's recovering our original message. So the two things we need to do are, remember what we're trying to do is to recover this envelope. So the first thing we want to do is to split the top bit from the bottom bit. So that process is called rectification. Okay, so you can use a half-wave rectifier like that, or you can use a full-wave rectifier, but half-wave rectifier should be enough because you have a very high frequency carrier. So what you want to do is, once you have rectified your signal using this diode, you want somehow to trace that peak. So we use a capacitor to do that. And this combination of R and C gives us our tuning circuit with a time constant of RC. Okay, so you see the demodulation circuit is really, really easy. So here what you have coming in is your AM signal, and what comes out from these two terminals is your message signal, or a version of your message signal. And all you need is a low-pass filter and a rectifier. Okay, so that's your low-pass filter, and that's your rectifier. And that is what we're trying to recover. So again, you've got your rectifier and your low-pass filter. So what happens, so this has been zoomed in to exaggerate, but what happens is that the capacitor charges up and then discharges, charges to the peak and then discharges, charges to the peak and then discharges. So what we're actually recovering isn't the original message, it's not even the envelope, it's this distorted form of the envelope, which looks a little bit like our original message, but it contains these ripples. Okay, so these ripples are a result of your capacitor charging and discharging. Now, it's important that the value of your capacitor or your time constant, RC, is chosen so that 1 over RC is between the carrier frequency and the message frequency. If your time constant is too big, then your capacitor will discharge too slowly, and then you'll miss all this. And that isn't good. That's introducing further distortion. If your time constant is too short or too small, you'll have it discharging too fast. And what that does is introduce deeper ripples, and that, again, is undesirable. So ideally, we want our time constant to be somewhere between 1 over FC and 1 over FM. And you need to reverse these inequalities. So RC would be much smaller than 1 over FM and much larger than 1 over FC. So what that symbol means is much larger, not just larger. So it can't be close to FM or close to FC. It needs to be very far away from both. Okay. So again, this is the implication of that. So if we chose RC such that its value was too big, then the capacitor would discharge too slowly, and it would miss this part of the envelope. So that is bad. That is a form of distortion. And another form of distortion is this this deep rippling effect, which would happen if our RC was too small. And there's a useful set of animations that you can look at. So this first website might not exist anymore. I've tried to load it, but it's failed. I'm not sure whether it's because it was Flash or Java wasn't working on my computer. But this one does work. So this one does work, and that gives you this little interface. I'll see if I can show that to you right now. There, so it needs a subscription, but it'll allow me a few seconds to play around with the time constant. So if the time constant's too small, then you have a deep ripple. If it's too large, then you can see that you're missing parts of the envelope. So that just allows you to experiment with that. So maybe spend a few seconds playing with that. Okay. That's all I wanted to say about the demodulation of AM. Now I want to speak about the power consideration. So remember when we said DSB-LC, really the L is important. We are very conscious of the fact that there is a large power wastage in the carrier. We keep saying the carrier contains no information. We've repeated it again and again. The carrier contains no useful information. So having a large carrier isn't good because it's wasteful. So if you think about the power that's being transmitted, there's three components to that. There's the power in the lower sideband, there's the power in the upper sideband, and there's the power in the carrier. So you've got these three components that make the signal. Now the only useful bit is the upper and lower sideband. And you could argue that it's wasteful in terms of bandwidth because you're repeating the same information in upper and lower sideband. But if we simply talk about the power, there's a lot of power that conveys no information in the carrier. And then there's power in the upper and lower sideband. So if we're going to talk about the efficiency, then we talk about ratio of powers. So let's just spend a few minutes talking about what do we mean by power. So when we talk about a simple sine wave, then the power of the sine wave is, remember, the average power of a signal is 1 over t integral of 0 to t x squared of t dt. And if you do that for a sine wave, you end up with a squared over 2. So if it was not a sine wave, then it wouldn't give you that. But for a sine wave, it would give you a squared over 2. So that's similar to saying that it's the RMS value. So what's the RMS value of, if we said x of t equals a cosine omega c t? Then the RMS value would be a over square root of 2. So RMS, the R stands for root. So the mean square value is a squared over 2. So it's that squared. Okay, so if we had a sine wave of amplitude 10, so if x of t was 10 cosine omega c t, then the power of this signal would be related only to the 10. It wouldn't have anything to do with omega c, so the power would be 10 squared over 2. All right, so that would be your answer. Now, thinking back about AM, and in particular we're thinking about, let's talk about general AM. So mathematically, remember we said AM is where you have a carrier term, you have a message, and you have, this is your DC clamping, and this is your modulation index. All right, so we're talking about here single tone AM. That means your message is a single tone. All right, you might think, what happened to the amplitude, AM? Well, AM got multiplied by K, and all of that got included in that term there. So we'll just use M as the amplitude of your cosine. So when you multiply this out, you end up with a cosine term. And then you have these product terms. So cosine, cosine. So cosine omega ct multiplied by cosine omega mt. So when you have products of cosines, so cosine A, cosine B, that'll give you half cosine of the sum plus half cosine of the difference. I don't know what that's doing there. So here you have half cosine of the sum and half cosine of the difference. So omega c plus omega m, omega C minus omega m. And if you think of how that would look in the frequency domain, then your carrier term here is this term here. Omega C minus omega m is your lower sideband. And omega C plus omega m is your upper sideband. And this is your original message. So this is m of t, or m of omega. So this is your original message, but it doesn't exist at the same time as your bandpass signal. Okay, so I've included it, and you'll often find this in textbooks, included on the same axis, but they don't exist at the same time. Why? Because this is your bandpass signal. This is what you actually broadcast, whereas this is your baseband signal. So let's just put that dotted, because it doesn't really exist. It's only there to show you that you've had a very low frequency that's been shifted up to a very high frequency. So that could be in tens of kiloradians per second, and here you'd have hundreds of kiloradians per second, because omega C will be 50 to 100 times omega m. So this is going to help us. Now we've broken down our AM signal into these three terms, 1, 2, 3. We can then see where is the information. Remember, we said all the good stuff is here. All the message that we're trying to recover is here. Whereas this, that's wasted. That's your carrier. So to calculate the efficiency, remember we said it's a ratio of the useful information divided by the total, or the power of the useful information divided by the total power. Okay, so quick question. If you have a carrier term like that, what is the power? What's the power of this term? So you can see clearly we would be looking at the amplitude AC, and it would be AC squared over 2. So that's how you would calculate that. If we now look at the sidebands, you might ask yourself, well, what's the power of the sideband? And that's the next question. So the power of the sideband, you would be looking at this, because this is the coefficient. So remember when we said 10 cosine omega CT? So this is the equivalent of R10. So what you want is half of that squared. So it's half of half AC times M squared. So that's half times 1 over 4 times AC times M squared. So that's that. Okay, so it's fairly straightforward to calculate the power of the individual components. Now what we can do, now we know the power of each of the components. We know the carrier has AC squared over 2 power, and we know that these sidebands each have that much power. So we got that from here and from here. So half AC squared and 1 over 8 M squared AC squared. So now we're going to use this information to calculate the efficiency. So power efficiency is the ratio of the useful power over the total power. The useful power is the sideband power, and it's the total sideband power, just to be clear. So it's both the upper and the lower sideband. So it's 1/8 of M squared AC squared twice. So it's like 1/4 of M squared AC squared. And you divide it by the total power, so that's where you add the carrier component. And you can cancel AC squared and then multiply all by 4, and that'll give you this expression here. So the power efficiency of AM is a function of the modulation index. So if you change the modulation index, the power efficiency will change. So, if you just think about the implication of this, think about how can we maximize the power efficiency. So remember we said m at best is 1. So if m is 1, then 1 squared over 2 plus 1 squared is 1/3, which is 33%. So that's quite low. So that means that 66.7% of the power that we're generating, or the power that we're transmitting, is wasted. Now we say wasted between inverted commas because it actually isn't wasted. It doesn't contain useful information. But remember when we spoke about trade-offs in the design of communication systems? Power at the source, so at the transmitter, is readily available. So there's plenty of power here. So this is a radio mast with all these antennas, but power is available here. It's at the receiver where there is no power. Okay, so remember we looked at the foxhole radio, we're looking at an envelope detector with no power. There's all passive components, there's no local oscillator, there's no power supply. So this is a version of that, okay? It does have a power supply there, but this is a low-cost AM receiver. And at the receiver, being able to use the power contained within the carrier is a bonus. So even though AM is inefficient, it's inefficient by design. It's intentionally inefficient, if you like, in the sense that the power is still useful. It's useful because it helps power the envelope detector. So what you have is the ability to track this envelope, and we wouldn't be able to do that if we didn't have this carrier component. So the carrier component allows AM receivers to be very simple. It allows them to be low cost. It allows them to be simple enough not to need a local oscillator. Okay, so this is a disadvantage of AM compared to other modulation formats, but it's also a feature of AM that the receiver can be simple and low cost. So, in summary, what have we learnt today? We've learnt that with DSB large carrier, we have 2 sidebands in addition to the carrier, and demodulating them is really simple. There's poor power efficiency, which is at most, or at best, 33%. We also know from last time that the bandwidth of AM is twice the bandwidth of the original message. Okay, so that's because you have your upper sideband and your lower sideband. And AM, where is it used? We use it for AM radio broadcasting, where you have one transmitter where power is available and many receivers where power might not. Okay, and AM is generally in the kilohertz region. So when people talk about long wave and medium wave radio, that's where they're talking about AM. So we're talking about sort of 50 kilohertz to around 500 kilohertz. So that's a summary of today's lecture, where we spoke about non-coherent or asynchronous demodulation, the envelope detector. We spoke about the power of the different components, and we spoke about the efficiency. Next, we're going to talk about other types of analog modulation, and I'll actually release that lecture tomorrow. So I hope you found that helpful. Until next time, stay home and stay safe.